Okay, we're going to find the 20th term of this geometric sequence, which means we need to define it first. We need to find the equation, the explicit formula for it, and then use that explicit formula to our advantage. I'm going to label my pieces. A sub 1 equals 2. I'm multiplying by 2 every single time. So A sub n equals 2 times 2 to the n minus 1. And then if I wanted to find the 20th term, we would do 2 times 2 to the 19th power. If you still don't know how to do exponents that aren't squared, look for the caret. So on your calculator, there's this little up arrow, which is we call it a caret. And so that's if you press 2 times 2 caret 19, it'll make it look like that, if you can read that in very, very blurry calculator mode. I'm going to write this in scientific notation because my calculator gave it to me in scientific notation. Remember when you have the E at the end, that's your scientific notation in disguise. So we've got 1.05 times 10 to the 6th power. Okay, so here is a common application of your geometric sequences. At 8 a.m., 1,000 milligrams of medicine is administered to a patient. At the end of each hour, the amount of medicine is 60% of that present at the beginning of the hour. What portion of the medicine remains in the patient's body at noon if no additional medication has been given? So our very first, so we start at 1,000, and at the end of the first hour, it's already 60% of 1,000. So be very careful here, especially with these application problems. Keep in mind that your first term is when you've plugged in 1 for the time that has passed. And if you plug in 1 for the time that has passed here, that means that you're talking about at the end of 1 hour. So your A sub 0 is 1,000. But that's not your A sub 1. Your A sub 1 is 1,000 times 60%. Remember that 60% as a decimal is 0.6. which will also be your common ratio, which is 600. So that is your A sub 1. Your textbook wants you to keep 1,000 as A sub 1 and then just count the hours passed as adding on an additional hour. I don't think that makes sense. So I would encourage you to do it this way. Think of like your initial amount as not your A sub 1, but your A sub 0, and then always calculate first your A sub 1 from that. Okay, so that's your A sub 1, and then your common ratio is .6. So if I were to then make a formula for that, A sub n equals A sub 1 times your common ratio to the n minus 1. Calculating at the end at noon, at the end of noon or at noon? At noon, which is at the end of the 4th hour. 8 to 9, 10, 11, 12. Yeah, the 4th hour. So we're finding A sub 4, which is 600 times 0.6 to the 3rd power. Which is 129.6. So if you're following along with your textbook, you'll notice that they set up this equation differently, but they got the same answer. So I would encourage you to go, if you've been taught this in another class, so like if you were Mr. Fine's class before you came to this class, or Ms. Zaffron, they might have taught it to you a different way. Go with the way that you feel comfortable with. But this is how it makes sense to me, is that at the end of the first hour, we've already passed the initial amount. And so your A sub 1 is not what's given to you. Okay, so that is how much is left in their system at noon. 129.6 milligrams, which is, we can talk for a long time about the benefit of understanding how much medication is left in somebody's system at a certain amount of time. Obviously, overdoses are a really terrible thing that can happen really quickly if you're not keeping track of medicine and its depreciation or its degeneration in a body over a certain amount of time. And if you're talking about trying to keep a proper balance compared to their weight, and figuring it all out. This is definitely a part of calculations that happen on a regular basis. They just tend to happen on a computer now and not on somebody's piece of paper. But they used to happen on somebody's piece of paper. And somebody has to program the calculator or the computer to do it. Okay, a second dose of 1,000 milligrams is administered at 10 a.m. What is the total amount of the medication in the patient's body at 12 noon? Okay, so again, I'm looking at what your textbook does, and it doesn't really make a whole lot of sense to me. So I'm going to talk about, we need to figure out how much is left in the patient's body at 10 a.m. and then add 1,000 to that, and then follow the depreciation with a second equation. It's a little bit more work than how your book wants you to do it, but it's how my brain is making sense of it. So I'm first going to figure out how much is left in this person's body at 10 a.m., which is 2 hours after it's been administered. So I'm going to find out what is A sub 2. A sub 2 is 600 times 0.6 to the first power. Which is 360. So then if I was to add 1,000, I get 1,360 at 10 a.m. So at 10 a.m. is how much is there. An hour later would be your A sub 1. So I need to then call this A sub 0. So my new A sub 1 is going to be 1,360 times 60%. Which is 816. So if I wanted to talk about how much is left at noon, A sub 1 is now 816 times 0.6 to the n minus 1. How much is left at noon is 2 hours after that dosage. So then A sub 2, which you could then take 816 and multiply by 0.6, but since we're practicing using formulas, here we go. 816 times 0.6 to the first power, which is 489.6. The same answer that your book got, milligrams, but just in a different way. You have to restart the depreciation or the degeneration process when a new amount of the drug has been administered. So there you go. Okay, so we're going to split up our notes now and talk about compound interest. Your homework today does not talk about it, but I do want you to make sure that you learn about this before the next time we see each other. Compound interest is the number one way of applying geometric. Actually, no, we're not going to do that.